In this example, we are going to use the divergence theorem to prove this statement about the integral of a Laplacian of a function over a solid region in three-dimensional space. And there's a lot of symbolic stuff going on here, so more than anything, we just have to unpack what all these symbols mean. So this right here, this is a definition of a normal derivative. This is written in kind of weird notation because it looks like a partial derivative the way it's written, but actually this is a directional derivative. So a better way to write this would probably be d sub n of f, because remember the definition of our direction, well, one of the consequences of the definition of our directional derivative from way back in chapter 14 is that the directional derivative can be computed as the gradient of the function dotted with the direction vector. And we know that the unit normal vector to a surface, the outward pointing unit normal, is always a unit vector, right? The key there is that it's a unit vector. So it picks out a direction for us. And so this right here is the key either way. No matter which way we write it, whether we write this symbol or this symbol in here, what we're actually going to compute, or we're going to talk about here, is that this should be equivalent to, so this notation right here is equivalent to just swapping out with this definition in some sense, right, of the directional derivative. And of course, this right here, once you now have a vector field dotted with a normal vector, the outward pointing normal vector, ds, this is just a flux, right? So this is the flux. As far as a double integral goes, this is the flux of the gradient field dotted with ds. And so this is not any proof or anything. This is literally just unpacking the definition here. And what we want to do then is show that when the divergence theorem applies, so really the divergence theorem here is all about the region E, right? So the region E needs to be a simply connected bounded region in space that it's bounded by a simple closed surface, right? As long as that hypothesis is satisfied, then we want to show that the divergence theorem when applied to this kind of a function gives us this answer, right? Well, let's unpack the definition of a Laplacian then. So this one's not given to us here because we've already studied Laplacians. But remember, the Laplacian of f is the sum of the squares of, the sum of the second derivatives component-wise. They're not squares. The notation looks like squares, right? But it's the sum of the second component derivatives. And on a three-dimensional function, it looks like this, right? A function that works in 3 dimensions. But remember that in our vector notation, we can write this a little bit differently because this is actually the divergence of the gradient vector, right? So the Laplacian is the divergence of the gradient vector, and that is good to know because the divergence theorem, right? We know that the hypotheses on the region itself for the divergence theorem are met, and now we actually have a divergence field if we write this function as a divergence here. And so let's just make this change right here, and we write the triple integral over E of the Laplacian of a function f dv. Well, what does it mean to be a Laplacian? It means it's the divergence of the gradient field. So this is now triple integral over E of the divergence of the gradient of f dv. That's literally just changing the symbols. We haven't done anything here. But at this point, we can apply the divergence theorem, right? So the divergence theorem applies. This applies. And what does it tell us, right? It tells us that the integral of the divergence of this vector field f is equal to the flux of f across the boundary. So the double integral over E of the divergence of the gradient field dv, this is equal to the flux of the gradient field around the boundary, right? But look at that. That is exactly what we've unpacked up here as the right-hand side of our equivalence, right? And so I'm just going to rewrite this where it came from, which is that this is equal to the double integral around the boundary of this normal derivative, different notations for this, but the normal derivative along the surface. And so just by the divergence theorem, literally just by unpacking what the notation means, we see that this theorem is true. And so to integrate up, you can consider this theorem as telling you two different things, right? Every equality is a two-way street. To integrate up the divergence of a gradient field, so a Laplacian of a function, you can just take the flux of the gradient field, right? Or if you needed to take the flux of a gradient field for some reason, so your problem was talking about the flux of a gradient field, you could do that by taking the Laplacian of the function and integrating it up over the entire solid region.